The emptiest regions of space are actually boiling with activity. You won't find true nothingness anywhere in nature. Look past the stars, into the black between galaxies. Physicists call that place the vacuum, not empty void. It matters because this vacuum shapes forces and expansion. Tiny events there change how atoms bind and light travels. The mechanism is strange but measurable through subtle effects. Particles wink into existence, borrow energy, then vanish. We detect their fingerprints in laboratory forces and spectra. So tonight, we will look at that restless nothing. By the end, emptiness will feel alive and relevant. When you picture empty space, you likely see blackness and silence. In physics, a vacuum means an absence of matter and particles. That definition sounds simple, but modern theory paints a different picture. Why care? Because the vacuum influences every force and interaction. The reason is fields permeate space, even without particles. Those fields can store energy and fluctuate unpredictably. Mechanically, quantum fields have lowest energy states, but not zero energy. Those fluctuations induce transient particle pairs and shifting field strengths. An example is a sealed chamber pumped near perfect vacuum, still showing small energetic noise. Measurements of atomic spectra reveal shifts caused by the vacuum background. So the basic idea is, empty space hosts fields and small activity still matters. Quantum physics replaces particles with fluctuating fields that fill space. This view means vacuum is a seething field bed, not emptiness. That matters because fluctuations change physical constants, slightly altering interactions. The mechanism involves virtual excitations popping out for fleeting times. Those excitations exchange energy with real particles, modifying forces in measurable ways. For example, atomic energy levels shift due to vacuum fluctuations, observable in lab spectroscopy. In one famous measurement, hydrogen energy spacing matched predictions, including vacuum effects. Quick mental image. Invisible waves rippling through a calm sea, barely visible, yet affecting floating leaves. Net result, the quantum vacuum is active and experimentally relevant. Virtual particles are short-lived disturbances of the vacuum fields. They appear briefly, then annihilate back into the field. This is important because they mediate forces and screen charges over distance. Mechanically, when two charges interact, virtual particles shuttle momentum between them. The same process slightly alters how light travels near materials and creates tiny forces. A concrete example is the Casimir effect, where two plates in vacuum attract slightly. Experiments measured this tiny force, matching quantum predictions to high precision. So virtual particles leave measurable fingerprints, proving the vacuum's restless nature. Even empty space holds energy, called vacuum or zero-point energy. That energy contributes to spacetime dynamics and may affect cosmic expansion. The mechanism is that every field mode stores a baseline energy, summed across modes. Those sums produce a large theoretical energy density, though observations show a far smaller value. An illustrative number, naive theory predicts energy densities far beyond what we measure, by many orders of magnitude. Astronomers measure cosmic expansion rates that imply a tiny but non-zero vacuum energy. Bottom line, emptiness carries energy, and that energy has cosmic consequences. As the universe expands, more vacuum volume appears between galaxies. If vacuum energy density stays constant, total vacuum energy grows with expansion. That growth accelerates expansion, creating a feedback loop across cosmic history. Mechanically, general relativity treats energy as a source of spacetime curvature, so vacuum energy curves space. Observationally, supernova surveys and cosmic microwave background measurements indicate accelerated expansion. One example, distant supernova brightness showed the universe's expansion speeding up, implying a repulsive component. So empty space might be driving the universe's acceleration, not matter or radiation. Realizing vacuum is active forces a rethink of reality's building blocks. The universe looks less like billiard balls and more like interacting fields everywhere. This perspective matters because it changes how we model particles and forces. Mechanically, particles are excitations of underlying fields, not standalone objects. An example is the electron, which is a ripple of an electron field spread through space. That view explains particle creation in high-energy collisions and fusion processes in stars. So the deeper picture. Fields fill space, and particles emerge from those fields' excitations. Despite progress, vacuum energy remains a deep mystery in physics. Theoretical estimates and observations differ dramatically in size. That mismatch matters because it signals missing ingredients in our theories. Mechanically, cancellations or new physics might reduce the vacuum energy effectively. Some ideas invoke symmetries, while others propose dynamic fields evolving over time. For example, a hypothetical field could slowly roll, reducing the net vacuum energy today. But experiments have not yet confirmed any of these ideas. Net result: the value of vacuum energy is one of physics' biggest open problems. Space behaves like an active background, not a passive stage for events. It stretches, it fluctuates, and it interacts with matter continuously. That matters because it participates in dynamics rather than merely hosting them. Mechanically, spacetime dynamics feed back with field energies, producing observable effects like gravitational lensing. An example is cosmic microwave background patterns, which record fluctuations in early space and fields. What to remember: the universe unfolds within a dynamic background that shapes outcomes at every scale. New instruments and experiments could finally reveal the vacuum's deeper nature. Telescopes, particle colliders, and precision measurements will probe vacuum fingerprints. That matters since discovery might rewrite physics textbooks in cosmology. Mechanically, improved detectors can measure subtle vacuum-induced forces and survey expansion more precisely. A concrete prospect is next-generation surveys mapping dark energy behavior across cosmic time. So the future may show that nothing is profoundly something, changing how we define reality. Empty space is not empty. It is active, energetic, and deeply connected to reality. What we once called nothing may be one of the most important things that exists. That is the calm takeaway to hold. The universe hides its deepest secrets in plain emptiness, not only distant objects. If emptiness sculpts reality, our curiosity should focus there. If you enjoyed this exploration, consider subscribing for more concise science dives.